Hello and welcome back to this course on programming in Rust. So in this video we're going to cover asynchronous programming, which is how a single thread can juggle thousands of tasks that spend most of their time waiting around for something to happen. A good example of this are network requests, which sits and waits for a reply. Async is a different tool from the threads that we use for concurrency, and picking the right one for the job is an important thing to know when programming in Rust. Okay, so I've created a new project called Async Programming, and we're going to do our work in this main.rs file. I'm going to go ahead and delete this print line statement, and we're going to start to write a async function, which you write by putting the async keyword in front of an ordinary function. So let's see this in action. Alright, so here's a part that actually trips people up when they first use asynchronous programming. Calling fetch data doesn't actually run it. Nothing really happens at all. Instead, what we get back is a future, which is a value that stands for work that hasn't happened yet. Think of this like a receipt. The receipt isn't the meal that you're eating, it's a claim on a meal, and you have to hand it back to get the real thing. And handing it back is that .await on the end of that call. Await tells the runtime to run the future to the end and give you the value inside. Here's the clever part though. While the future is stuck waiting on something slow, await lets the thread step away and get on with other futures. Waiting without blocking. That's essentially the whole idea behind asynchronous. So we have async functions now, but nothing can run them yet. The standard library gives you the definition of a future, but it doesn't actually give you the engine that drives one. That engine is called a runtime, or an executor, and in Rust you bring your own. So what does the runtime do? It's the scheduler that takes all your futures and decides who runs them, handling the thread straight to another task the moment one stops to wait. Now, a go-to choice is a crate called Tokyo. It's an external crate, and it's quite popular, and it ships async versions of the everyday tools that you'll want, things like network sockets, timers, and file access. So what are we going to do? Just open up our terminal again. I'm actually going to cd into my project, and then we're going to go cargo, add Tokyo, not like the capital of Japan. And then we'll put features full, which will give us the full feature set. So I'll actually open up my cargo.toml file, and we can see that Tokyo has been installed. Now let's work in our main function. We're going to add a Tokyo attribute to the top, which will boot the runtime and let the main function itself be async. So let's type the following. Okay, let's open up our terminal again. I'll just clear that. And we're going to run. And there we go. So essentially what happens, I'll just get out of the terminal, is that main awaits run. Run then awaits fetch data, and the runtime drives that whole chain right to the end. So we get our printed data here returned to us. So awaiting one future, then the next, like this, is one at a time work. You're still stuck waiting for each one to finish before the following one even starts. What we want instead is to let several futures make progress at once, so all that waiting happens together instead of one wait after another. And the simplest way to do this is by using a macro called join. So what I'm going to do is just add some things to this file, just to show you what this actually does. Okay, so join takes a handful of futures and drives them together, which is what we're doing here. The moment one stops to wait, the runtime will work on the other, so their waiting overlaps instead of stacking up. And here's the part worth noticing. This is two things happening at once on a single thread with no extra threads anywhere in sight. That overlap is the reason async is such a good fit for work that mostly waits. Join is great for when you know your future's up front, but sometimes you want to start a job or spawn a task, let it run on its own, and then collect the result later. Here's how it looks, and it goes inside any async function. So I'm just going to go ahead and write the following. So in this method, you hand Tokyo spawn a block of async work, and it hands you back a handle. The task starts running straight away, and whenever you're ready, you await that handle to get its result. The unwrap is here because a spawn task can fail on its own, so awaiting it gives you a result to check. At this point, you can go back into your main, and we can actually point it at spawn task. Now let me open up the command line, and we'll just clear that. And if we run it, we should see our data being printed back out to us. Now this looks a lot like spawning a thread, and the mental model is still the same. What's different is the wait. An async task is far cheaper than a real operating system thread. Where a few thousand threads would overwhelm a machine, you can run hundreds and thousands of these tasks and barely notice. Now, a final piece of vocabulary that we need to cover is a stream. If a future is a single value that shows up later, a stream is a whole sequence of them, arriving one after another over time. It's essentially the async version of an iterator. Instead of looping over items that are already sitting there, you await each item as it lands. A feed of incoming network connections is a perfect example of this. Streams live in their own crate called Tokyo Stream. So what I'm going to do, open up my terminal, clear the output. We're in the async programming project. So cargo add Tokyo-stream. Get out of the terminal, open up the cargo toml file, and I can see that it's been installed. So let's go back into the main.rs file, and we're going to create a simple example for using one. So the first thing I need to do is actually bring in Tokyo Stream. Come down to the bottom of the file, and I'll write the following. So let's take a look at this loop. It's a while let loop, and each value comes back from calling next and awaiting it. So it reads almost exactly like looping over an iterator, except each item is awaited as it arrives. So if I come back up to the main method and write print numbers instead, I'll open up the command line, clear that up, and run it. We should see the numbers 1, 2, and 3 being printed out to the console. Now the big question that you might be asking, when do we use async and when do we use threads? The rule of thumb is short. Threads and libraries like Rayon are for heavy computation that needs serious CPU work, like our fractal renderer. Async is for work that mostly sits and waits, like network requests. And in the next video, we're going to build a web crawler where we're going to be almost entirely waiting on the network to make calls, which is exactly why async suits it so well. But before we do that, let's recap. So in this video, we took a look at asynchronous programming in Rust. We learned that an asynchronous function hands something back called a future. Calling it actually doesn't run anything. You'll get a value that stands for work that is still yet to be done. Await runs a future and then steps aside. It drives the future to its value, and while that future waits, the thread gets on with other work. We also learned that futures need a runtime. They can't run by themselves, so a runtime like Tokyo schedules and drives them, which is what that Tokyo main attribute sets up. We also learned that join overlaps the waiting. It derives several futures together on one thread, and a stream carries the same idea to items that arrive over time. Now, comparing this to concurrency, we learned that async waits while threads compute. We should pick async when the work mostly waits, and we should use threads when it mostly does heavy computation. So in our next video, we're actually going to put this into practice. We're going to build a concurrent web crawler, one that fetches loads of pages at once instead of plodding along through them one at a time. So if you like this video, give it a like. If you want to see more videos on Rust, don't forget to subscribe. Any questions, please put them in the comment section below, and all the resources, including the code that we wrote in this lesson, will be in the video description. Thank you so much for joining, and I'll see you in the next one.